So we've seen a few different ways of showing that triangles are congruent, but the real power of using congruent triangles doesn't come simply from saying that the two figures are congruent. The power of using congruent triangles comes from something that is true about congruent figures generally. For example, when we have the side-side-side postulate, we know that three sides of one triangle are congruent to three sides of another triangle. And in this case, we can say that triangles ABD, or ABC rather, and triangles XYZ are congruent. But when we first started talking about congruent figures, it's not just the segments that are congruent. Once we know that the triangles are congruent, we also know that the angles in those triangles are congruent. So angle A is congruent to angle X because they are congruent figures. We know that angle ABC is congruent to angle XYZ because we have two congruent figures. And when it comes to triangles specifically, this property, that once we know that triangles are congruent, that we can say that all of their other corresponding pieces are congruent, is something that we often abbreviate as CPCTC. Corresponding parts of congruent triangles are congruent. So go ahead, pause the video, copy down the bright yellow and blue text there, that's CPCTC, means that corresponding parts of congruent triangles are congruent. Come back, we're going to see two quick examples of that. This is going to be a really short video, and then we'll wrap up. So if we look at two of the proofs that we did in the video about congruent triangles, one of the things we were asked to do is show, using the side-side-side postulate, the triangle ABD is congruent to triangle CBD, and we did that by using the definition of midpoint, as well as this reflexive property shared side. So we've gone through the proof. We're just to sort of wave our hand. We've already seen this. We're not going to copy it down here again. So we've gotten through the proof, and now we're down to the point where we've said a triangle ABD is congruent to triangle CBD because of side-side-side. Well, now we have a lot more things we can say. Maybe the end of the proof wasn't that we wanted to prove the triangle ABD is congruent to triangle CBD. We wanted to prove that angle ABD is congruent to angle CBD. And once we do that, once we have side-side-side, we can say that that's true. Those are corresponding angles in the two triangles. They exist between the congruent sides of the isosceles triangle and the reflexive side of BD that's shared in blue. So here now we can say angle ABD is congruent to angle CBD because of CPCTC. That is the reason that's going to go into our proofs. Well, BD now, just because we know that, BD cuts angle ABC into two equal subangles. So we can even go one step further and say that in our statements and reason here, BD bisects angle ABC. That was really sloppy writing right there, but you know what I mean. And that's because of the definition of an angle bisector. So CPCTC allows us to say a whole lot more than just the fact that two triangles are congruent. If we didn't have CPCTC, we couldn't say that the angle is bisected. The same thing is true for the SAS postulates, where we wanted to say that MET was congruent to JET. We didn't know anything about it, but once we got to there, we could say that angle M is congruent to angle J, because they are the corresponding pieces of the triangles. And if we know that these two angles are congruent, suddenly MTJ is a triangle that has two congruent angles. So that means the sides opposite those two angles are congruent, TM and TJ, because of the isosceles triangle theorem. And therefore, that triangle MTJ is isosceles. That is part of the definition of an isosceles triangle. So CPCTC gives us access to a whole lot more information than we had before. Pretty much any time we use congruent triangles in proofs, it's because we want some extra information about a piece of the triangles that we didn't know originally as part of the congruence postulate, and that's where CPCTC comes in.